Okay, calculate the pH of 0.1 molar of this stuff, show you're working. So, always do your chemical equations first, complete dissociation, so we've got that going on. So how many moles of this have we got? So number of moles of BOOH is, it's 0.1 molar. Okay, so it's concentration, C equals N on V. So number of moles of C times V, we'll assume 1 liter. Okay, so we're just going to assume 1 liter. So the number of moles for 1 liter is 0.1 moles. So 1 mole of BaOH is to 2 moles of OH minus. So 0.1 is to X. So X equals 2 times 0.1 equals 0.2 moles of OH minus. So that concentration, or 1 liter, is 0.2 molar. So I've just worked it back to that just to get the equations. So I don't know why they give us a little room when they ask so much, but that's all right. Okay, so the POH equals negative log of the OH minus concentration. Okay, so that, getting the so negative log of 0.2. All right, so 0.2, log 0.2, so that's 0.699. Stick with three figs for these things, and so pH equals 14 minus POH equals 14 minus 0.699. So just add 14 to that, and that'll give us 13.3 to 1 decimal place. Okay, question 22. Draw the structural formulas for 2 structural isomers of pentane and name each isomer. So there's 1 and there's 2. Just 2, any random 2. Could just put a methyl group over here. And then I could just put another 2 and put that in the middle. Is that going to be different? I don't know. Let's just draw the structurals just in case it's not okay. And just leave some room, just in case they are exactly the same thing. So put a methyl group over here. 1, 2, 3, 4, 5. Okay, so 1, 2, 3, 4, 5. Thanks for using the blender while I'm doing the video. Yeah, I don't think there is going to be. I think they've done this one so that there are no other options. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. I don't think there's anything else, because if you do anything else, it's actually just another version of these things. So I think that's all there is. Now, always draw in all of the extra bits and then count them up too. So each carbon has 4 bonds, so don't take the risk. Show them all clearly. Don't just get lazy and write CH3, because some of them won't be CHs. Like that one's just a CH, that's a CH2. Making sure the carbons have 4 bonds. All right, so just double check the hydrogen. So there's 5, 10, 12. Oh, it's up here, sorry. So 1, 2, 3, 4, start from here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Start from here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we're all good. All right, so that's fine. So the UPAC name, this is now 4. So that's now going to be butane. And on the second carbon, the closest one in there, so it's 2-methyl. Yeah, that's a blender. 2-methyl butane, what you can hear there. So that's propane. So there is a 2, 2, so that's a 1, 2, commas, oops, 2, 2 dimethyl propane. No problems. Okay, question 23. A methyl ester of dipeptide hydrolyzes to form methanol and 2 amino acids. So we need to break this up. So there's a carboxylic acid and an amino group. So where would that be? See, carboxylic acid here. And an amino group? No. Possibly here. So that's the carbon here. And the main carbon here. So that's a carboxylic here. So the carbon has to have a carbon with the carboxylic acid OH come here, and then a H come here. And there is none of those bonds there. So let me work backwards a little bit. So there's, how many phenyl groups are there? There's not many there. Could be tyrosine or phenylalanine. So there's no OH there, so it must be phenylalanine. So we'll just work from there. So the phenylalanine, the CH2's there, then the C. So that's the central carbon. And then we've got this group out here. So we've got this side group here, we've got a hydrogen out here, we've got this bit forming the peptide bond, and we've got OOH. So that's the weird thing. So that formed the methanol, I guess. So that's fine. So we've got phenylalanine there. So we'll lock that in. All right, and then, so we've got phenylalanine there. That makes life a little easier for us because now we know we can just look for something that's got a carbon here, carboxylic acids here, hydrogens here. We're just looking for this group. All right, so if we're looking through, something with an extra carboxylic acid. So glutamic acid's there. That's got an amine group in it. And aspartic acid matches that. It's just got the CH, it's got the CH2 there. It's just got that bit there. Okay, so it must be phenylalanine and aspartic acid. All right. I'm just going to check before I move on. I know that's sort of cheating because I don't want to get... yeah, okay, so it looks correct. Aspartic acid, phenylalanine. So don't want to go up the wrong garden path. So this one here, I need that as well. So what I'm doing now is determine which amino acid corresponds. So now I have to work out which of the two of these goes up here. Now, I don't think you're meant to know this. Butanol ethanoic acid and TLC. So this is chromatography, so this is cellulose. And so cellulose. And so there's heaps of OH groups on there, so it's fairly polar. So the non-polar one is going to go up here. So I'm just going to say because TLC is cellulose with many OH groups, the polar amino acid, that's the shorthand, will move less, and the more polar amino acid will be carried by the solvent. More, and therefore spot A. Now, as we can see here, aspartic acid, now I'm just going to use the ASP amino acid, has lots of OH groups. Therefore, phenylalanine, which the symbol for that is PHE amino acid, has large nonpolar group, nonpolar phenyl. Therefore, A is phenylalanine. Phenylalanine, large nonpolar group. Okay. So I'm just going to check because I think the mark scheme, they screwed up again, like 2022. All right, they think they must be cutting and pasting. So the answer is isoleucine is a non-polar amino acid. Yeah, that's nice, but it's not isoleucine. So they must have copied and pasted from a previous question and just changed it to phenylalanine. Because it's not isoleucine. It does have a non-polar group, but so do the rings are also non-polar. So fine. The distance traveled by spice, simply distance traveled by isoleucine. So apparently this is isoleucine. So they've really sort of copied and pasted from other questions and haven't checked the answer, it seems. And phenylalanine. Okay, so now they've got phenylalanine. So isoleucine, who knows what that is? Phenylalanine's there. That's also non-polar. So the answer indicates isoleucine is non-polar. That's impossible because you don't know. Indicates that spot A is non-polar and travels similar distance, determines suppose. Okay, so that mark scheme is impossible. I have said that phenylalanine's a non-polar group. It'll move up. So my answer is way better. According strictly to that mark scheme, I've said A is phenylalanine. There's no way you can talk about isoleucine because they didn't tell you it's isoleucine. So God knows what the actual marking scheme really was and why they still publish a dodgy mark scheme. This is probably, this is a valid point. And the fact that it will move in a solid is a valid point. So it probably would have got a 3. If you stick strictly to a wrong mark scheme, they'd only get 1 out of 3, but they couldn't have done that, so God knows what happened there. All right, explain why the reference acid are included in TLC. So you can compare with known amino acids and so determine which amino acid it is. This is a silly question. They really shouldn't even put this in here. But that's fine. The mark scheme says allow trial to separate 2 big heavy. Yeah, okay, so we've got the mark. Okay, question 24. We've got this thing going on. Manganese is purple, copper's blue. We know that already, hopefully. Predict in which direction the electrons will flow. It's voltaic. Comparing the strength of the oxidizer. So you need to make mention of that word. Explain your reasoning. So we always put the half cells in there. So I'll just find them. So that one's copper's there and the other one's there. Okay, so that was more positive and this one's going to get reversed. All right, so I'll write that down. I'll write it here so it's going to be part of the answer. MnO4 minus plus 8H plus 5 electrons. This Mn2 plus, I hope it must be acidified, which they didn't say, did they? Oh, they did say acidified. There we go. So that's plus 1.51 volts. So the copper Cu, and that's plus 0.34 volts. All right, so this one must get reversed. So it's minus 0.34 volts. So it must be copper. Goes to Cu. 2 plus 2 electrons. All right. So this one is getting oxidized, so it must be the reducing agent. This one is gaining electrons, so it must be reduced, so it must be the oxidizing agent. Okay, so if that's the case, then the MnO4 is gaining electrons. So where is this? Where is the connection here? God knows. All right. So MnO4 is gaining electrons to go to Mn2 plus, and copper is giving off electrons, which makes sense, and that's going into solution. All right. So direction the electrons flow. Electrons will flow from the copper. Reduction occurs at the cathode, so that is reduction. They're losing electrons, so it's oxidation anode. From the copper anode to the platinum cathode. Did I write cathode in there? No, I didn't. All right. Predicted electron flow. Yeah, and I've drawn it as a picture as well, so that should give us marks as well as backup. This is because NnO4 minus cell is more positive, 0.51 volts, and so is reduced and the stronger oxidizing agent. Copper 2 plus is oxidized. That's copper is oxidized. Stop looking at this one, okay? Put a line through it. To Cu2 plus minus 0.34 volts. All right, determine the standard reduction potential of the EO. So therefore it is 1.51 minus 0.34. Don't really trust myself to do that. I'm going to use a calculator, I'm sorry. 1.51 minus 0.34. We get 1.71 volts. It's only worth 1 mark, so it'll just be the answer. So just move on with that. All right, predict the two qualitative observations. So movement in Earth. Okay, so the copper half cell shows with the flow of electrons and movement of ions. So copper will lose electrons, increase in Cu2 plus, therefore more blue. And MnO4 minus cell will gain electrons to decrease decrease MnO4 minus to Mn2 plus. All right, therefore less purple. Less purple. Okay, just doing a quick check on the mark scheme here. Identifies Mn as a stronger oxidizing agent. Did that correctly. It gains electrons. I've written it there, and I've written it there. Have I written it elsewhere? All right. Determines electrons will flow from copper to anode to platinum. Yeah, good enough. Yeah, no, I've actually said that. I've got this number correct, and just turn the page. Copper will increase, become more blue, and will become lighter. So I got those as well. All right. Okay, question 25. An equilibrium is formed between two different colors. So this one here is pink. And this one here is blue. All right. So you adding AgNO3 to an aqueous blue colored solution. So it's currently blue, and you've got this. So what's the effect of adding silver nitrate? So you've got to see whether the silver will precipitate. The nitrate won't do anything. The silver could potentially take something out, react. So silver chloride is suspicious. The silver often forms precipitates. So just go to the solubility table and have a look at first silver. We've got silver chlorides are insoluble. Anything else? Hydroxide? No, that's not really hydroxide. They're waters anyway. So silver chloride will come off. All right, so that's all we need to do. So, to explain your reasoning. Okay, so AgNO3 will go to Ag plus NO3. The silver ions will form AgCl precipitate. So that's going to decrease, all right? This will take Cl ions from left-hand side, and so push solid the equilibrium. To the left-hand side. So that will increase CO, that's a long one to write out, H2062 plus pink, and decrease COCl42 minus, blue brackets. So the solution will become less blue and more pink. All right, I just want to check the answer while it's up there. So antiphonous Cl will decrease. Yeah, we'll take it. Indifferent equilibrium shift to the left. Indifferent blue solution becomes lighter. Yep. So less blue, more pink. All right, so got those. All right, next bit. So far, all these questions are fairly easy. There's just a lot of them. When a sample of equilibrium mixture is put into hot water, the mixture turns more blue. So you've got pink, blue. It turns more blue with increased heat. Increased temp, more blue. So therefore, there must be energy on this side. So therefore, explain whether forward is XO and XO. So therefore, as push to right hand side with increasing temperature, heat input must be on the right hand side, left hand side, meaning reaction is endothermic. Okay, when the sample is put in hot water, the mixture turns more blue. Yeah, determine the forward reaction of the reaction is exothermic. Okay, so 2 marks, it should be fine with that. So identifies the forward reaction as being favoured. Push to the right hand side, yeah. In terms of forward reaction is endothermic. I've done that as well. Okay, so we've got those two. So question 26, you've got this equilibrium equation and graph. Identify if XY is a reactant or the product. It's like a year 9 question. It's over here. So XY is the product. What on earth? Well, year 9 students can get that one. Or year 8, maybe year 7, I don't know. Calculate the equilibrium constant. Okay, so I'll work a little bit too much into this one. I'll do a RICE for this. So we've got x squared, y squared, 2xy. So that is, just for understanding, 1, 1, 2. You could just jump to here. So initially, x squared is at 4, and this is 3.5, and this is 0. And then xy goes to 3, and this one goes to 2.5, and this one goes to 2. So that goes up 3, and that goes down 1.5 and down 1.5. So they all make sense. The graph's drawn correctly. So Kc is products over reactants. I'll just jump into that and use that for the next bit. So it's products, so that'll be x squared, products, xy to the power of 2, x squared, y squared. So those values are over here. So we've got 3 squared over 2.5 times 2. All right, so that is 9 divided by 5. So that should be 1.8 sig figs. All good. Check the answers, we're good. Is xy the product? Yes, surprise, surprise. Okay, the value of equilibrium. Describe whether the precision equilibrium favours reactants or products. Okay, so Kc equals products over reactants. So if Kc is greater than 1, which is 1.8, that means we have increased products and decrease reactants. So reactants go to products. We have increase, decrease. Therefore, equilibrium favors right hand side. All right, Maxime says equilibrium favors the products. K is greater than 1. Right hand side should be fine as well. Okay. Question 27. This compound reacts with arsenic acid, comes with nitrate. So check that out in your data booklet to form arsenic acid, this one, and nitrogen dioxide. Okay, determine the oxidation number of arsenic in arsenic acid. So we've got H3ASO4. So that's total of -8, and that'll be +1, so total +3. Arsenic acid is this. So we're looking for a total of +5 here. And so that'll give, let me see, +3. -2, -8. All right, so have I done a mistake here? Should be +5. So 3 plus 1s. -4. So the arsenic should be oxidation number of AS is +5. Now, going to the mark scheme, it has 3 times +1. We've got that. It's got arsenic by itself, which is fine. and then it's got 3 minus 2s. And so it's saying it's an O3. Ooh, it's arsenis, not arsenic. Oh my god, that's nasty. All right, so I actually got this one wrong, guys. I did this one. All right, and it's this one, so that is super nasty. So that one's actually a 3 minus 6, so you need a plus 3. Ouch! Give myself a 0 for that one. All right, yeah, arsenic. Ook. All right, let's hope I get the rest correct. Use half equations to balance the reaction. Okay, so let's be careful here. So we've got H3ASO3 plus nitrate ions reacts to form H3ASO4 plus NO2. All right, so we've already worked out, we'll do all these again. This will be plus 3, and this one will be plus 4. So this one here must be oxidized, and this one here must be reduced. So that's minus 2, minus 6, so that must be a total of plus 5. And that's minus 2, that must be plus 4. So that one goes down 1, so that's reduced. Okay, so that all makes sense. Hopefully I would have picked that up when I did this and reread it and redid all this. I'm assuming that would have happened for sure. That would have been picked up, that I read arsenis and arsenic. And hang on, there's 2 acids. Did I do the right acid? You'll have to trust me on that one, but that's an easy pickup, to be completely honest with you. All right, so oxidation. So just doing those. H3ASO4. So same number of ASs, that's fine. The next step, I have my own. You can follow these in any order really and still get it correct. So the next thing is we'll balance for the H pluses, their H strength, that's fine. So we've got all the H's balanced. Then we have to balance for the oxygens. Balance for the oxygens next. So we need an extra H2O. So H2O plus H3ASO3. And I'm just going to jump a step and go to the next step now, add it onto this. So we've got the oxygens right, we need 2 H pluses. So now the hydrogen's balanced, A's are balanced, O's are balanced. We need to balance charge, so we just put 2 electrons on there. Okay, reduction time. The reduction one is NO3. I wonder if I could just leave this in one line, that would be convenient. NO2, 3 minus. So H2O to balance the oxygens, 2 H pluses to balance the H's. Now I need to balance electrons. So I need another electron over here, so that makes sense. So there's overall no charge, and that makes sense. Now I'm going to times everything by 2. I'll do that as an extra step because we don't want to get too messy and confused. All right, so now I have this one and this one. Can cancel out the electrons. I can cancel this out to a 2. I can cancel out this to a 1. And I have to be really careful I don't make a transcription error. This is a pretty dangerous area here. So just rewrite this down. Plus 2NO3 plus 2H plus. And grab that one, H3ASO4. I think it's pretty important to circle. And even then, I don't really trust myself to get the answer right. So I'm just checking the mark scheme now. 1, 2, 2, 1, 2. Yeah, so that's all good. And I swear I would have picked that one up by then by using that. So just the very last thing, determine which species is reduced. Well, that's pretty damn easy because I already did the work of that. Why are you asking me there? You should ask me at the very, very top. That's not really the right place. Would have worked it out by then. Okay, so that's it. Okay, to question 28, last one. Sketch the titration curve when 20 mils of butylamine. So that is going to be 4 with an amine there. So that is, that's going to take a H plus, and that's going to go to, what's that? 2, 4, 6, 8, 9, C9, C4, H2, 4, 6, 9, H9, and H. That's going to go to acid, and let's titrate with HCl. So it's all 1:1:1. So that's useful. So if there's 20 mils of this, it'll take 20 mils of that. All right. So we don't have to do any of those calculations. Only have to do what we need to do. So we know there's 20 mils. So the other thing we know is that the pKa is the pH, the half equivalence point. So the equivalence point is going to be at 20. So we're going to use a pencil here. So that's going to be the equivalence point. And so we want it to react there. Now, when you've got a strong acid, I just use rule of thumb. So that's between pH 1 to 2 for strong. And then there's 4 plus or minus 1 for weak acids. And then strong bases 13 to 14. And then weak is 10 plus or minus 1. So they're just approximates. And this is a weak, so we're going to go there. So because the pH, the half equivalence point, which will be here at 10, the pH will equal the pKa, so we know it's going to be there. So that's a key point. So we won't go at 10, we'll go slightly up, 11. And it rapidly drops off, and then it's going to form a buffer because it's going to be a salt plus a weak base. So we can drop down here and then just go to a buffer, which is fine. And then we're going to end up at 1 or 2. So let's just go 1.5. And so we'll go across here when it's finished. Now the pH is going to be like halfway in between here. So it's going to be less than 7, of course, because it's a strong acid weak base. And that half of between here and here, so that's 10 and 1.2. So that's about, let's just say that's 9, 4.5. So let's just do it here. So the equivalence is the second equivalence point. We'll make it here, about here. So we're going to curve it up. So let's bring this close to the 20. Here, where's the 20? And then we'll pull it up here. There's about a half distance here. And then a half distance up here. So we'll start bringing it around here. So I might just just got to make that smooth. That's all. A bit dodgy that we have to draw this in. It's very unusual. This is so I'm going to do it like that. I want that to be even on both sides. That the big drop here. So more like that will be better. Okay, we should just do a real one because you can't really predict sometimes. So sketch a titration curve. So we've got a 10 here, we've got a 10 here. That's it. Doesn't need to label or annotate anything, which is really bizarre. Okay, so that's technically all you have to do. So if you go to the mark scheme, I didn't even ask to annotate anything. It's an S curve, yeah. Half equivalence point at pH 10 mils. So there's 20 mils there, 20 mils there. If you go up to 10, it is at pH 10, so there's a mark there. Equivalent point is less than 7 at 20 mils. 20 mils equivalence point less than 7. So yeah, that's fine. It drops off here and then goes here. So that's still, because it's still sort of here to here, which is about here, which is what we're aiming at. So hopefully that, maybe I should have dropped that and maybe been a bit better doing that, maybe. But they didn't really do it that much either. The initial pH between 10 and 12, that's pretty tight. And the final pH between 1 and 3, oh, they're so It's so random. All right. I have rules of thumb, which I've written here for this particular reason and for other similar questions to give you a rule of thumb, but it's only a rule of thumb. All right. So a bit of a dodgy question. Maybe the hardest one. Pretty easy paper. 2022 is way harder, but I haven't done paper 2 yet. But already the multiple choice on paper 1 were way easier. Really no tricks at all.